Hey guys, welcome to recitation number 12. So in today's recitation, we will be solving some problems involving series of real numbers. And I think these problems are from the worksheet that number 4. And most likely we'll solve problems from 5, 6, 7, and 8, and maybe some other two problems that I didn't have a chance to cover during the lecture. So, okay, we can get started. I'd like to start with a problem which is a little bit different than the last problem that I did in the lecture. And the problem has the following statement. So it's problem number 5, sorry, in the worksheet. And it says the following. It says that if, so let AN be a sequence. So this is be a sequence. Well, in my worksheet here, it's of positive integers, but in fact, no, it's of positive reals. A sequence of positive reals. Such that this series, the sum of AN cubed, this guy here, is convergent. And now we're asked to show that the series so AN over N is also convergent. All right, so this is the problem. Well, remember in the lecture we had something similar, and the problem, the similar problem that we had in the lecture was that instead of the AA cubed we had AN squared, but we have to prove the same thing basically. So maybe we can come up with a similar idea. So this is similar, and in that problem, we use the the arithmetic geometric mean inequality. So maybe we could do something similar here. So remember the same problem. So, so let me point out a remark here before I even go and start solving the problem. This is similar with the problem when this series was convergent. Implies that the series of AN over N is also convergent. Right? Well, in what way this was similar? Well, in fact, we use that AN squared plus 1 over N squared by the AMGM mean inequality, right? So by the AMGM inequality. So this was greater or equal than 2, so 2 AN over N. And of course, from now, and this implies that the sum, if we take the series of AN squared plus 1 over N squared, is greater or equal than to the sum of AN over N. But these two guys, this is the sum of two convergent series. So we have the sum of AN squared plus the sum of 1 over N squared. And both of these two guys are convergent. So these two both are convergent. Right. And therefore, by the inequality comparison test, it follows that, so by the inequality comparison test, it follows that the series an over n is convergent. All right, so that was the story for this problem, right? So for this guy here, so when this guy converges, it also implies that this guy also converges, right? So, but now in our situation, you see I have the fact that this guy is convergent, then it will imply that this guy is convergent. So maybe we would like to use a similar approach to this one. So what if we try something like, you see, you're tempted to use the same idea, right? Maybe I could use something like an squared plus 1 over n squared plus 1 over n, right? You know, when I apply the AMGM, I have 3 an over n, right? So why we can use a similar approach. In fact, let me delete all this and let me see. So we would like to see, let's use this approach. In fact, I already wrote it. And let me tell you why, if I want to use a verbatim approach, or like very, very similar to this one. So let's try it first, and let's figure it out why it doesn't really work. So we can try something like this. So an cubed plus 1 over n, n squared plus 1 over n. And by, again, the AMGM inequality, it follows that this is greater or equal than 3 an over n. But you see, what is the problem here? When I, so this will imply that this series, let's write it in this way. In fact, let me just write it like this: an cubed plus the sum of 1 over n squared plus the sum of 1 over n is greater or equal than 3 the sum of an over n. You see, I have no problem with this guy. So this guy is convergent. The same goes for this guy as well. But this guy diverges. So it's the harmonic sequence, harmonic series. So it doesn't work like this. So maybe I should do something that will make everything convergent. So maybe I could, instead of using this 1 over n here, maybe you see I can calibrate the exponents in some way so that the sum of that will be convergent. So this doesn't work. Nice try, but doesn't work. Okay, so maybe we should try something. And here we go. We can have the following idea. So let's write it. We can try something better. Such as, let's see, I'm going to write it in this way. Let me write it with a different color so that you can see it. An cubed. And pay attention now, I'm trying to fabricate 3 numbers so that I can apply the same idea with the AMGM for 3 numbers this time. But I would like to look carefully at the exponents of n. So instead of putting, maybe I should take something out from 2 and add it to the third exponent, which is 1. And of course, let's do it this way, so that also I can take something out in such way the AMGM will work just smoothly. And indeed, I can do this. Look at this guy here. So I can do this trick. And again, by the AMGM inequality, so AMGM inequality, this is greater or equal, let's be careful here, by 3 cube root of 3 of AN cubed times 1 over N to the 3 halves times 1 over N to the 3 halves. And this would be 3 AN over N. Wow, that's just beautiful. You see, this AMGM works just perfect. And now this implies that so this will imply that the sum of these guys, so this is nothing else than just 2 is greater or equal than 3 the sum of these, right? AN over N. So you see this series on the left hand side dominates the series on the right hand side. So if we show that this is convergent, then we're done. But this guy here is nothing else than just the sum of AN cubed plus 2 the sum of 1 over N to the power 3 halves. Perfect. Now it's quite clear what to do, what to see. This is convergent. And this guy here is also convergent, right? A harmonic series with exponent greater than 1, 3 halves is greater than 1. So therefore, by the comparison, so let's say, right, by the inequality comparison test, it follows that that the series is also convergent. All right, and that's it. That's the problem. We're done. So you see, it was tricky in this way. And of course, you can generalize this. And in fact, I'll leave it to you. You can prove this using some kind of holder or Cauchy-Schwarz, anyway, whatever. All right, so this is the first problem, problem number 5. Now there was another problem that I wanted to do. Let me number it with problem 1. Why should I put, it's problem 5 from the list, but it's problem 1 in our, and problem 2, again, which is important. It's pretty classic, but it's a beauty. I think you should know this. And the problem states as the following. So let N be a decreasing sequence such that decreasing sequence of positive reals, okay, that's of positive reals, such that the series converges. Show that the limit as n approaches infinity of n a n is 0. All right, so this is the problem. It's a very famous, I think this is due to Abel. It's an Abel criterion, so anyway. This is a very famous Norwegian mathematician, Niels Abel. Also these days there exists the so-called Abel Prize for which is awarded to mathematicians for outstanding contributions. It's pretty similar in nature with the Fields Medal. So let's look at this guy. And you see I have here the important thing that is a decreasing sequence and the series converges. Well, we said that we said that if the series converges, then the sequence AN converges to 0, remember? So remember that AN, the series of AN convergent implies AN will approach 0 as n approaches infinity, but not the other way around. So the other way around does not hold true. This is not true here. So I can find sequences that will converge to 0, such as, for example, AN equals 1 over n. I think we've discussed this. We have already discussed this in the lecture in such way that the series will not be convergent, will be divergent. You just take AN to be 1 over n. We have already seen this in the lecture. Okay. But now, not just that, you see, I want to prove something I want to prove even more. I want to prove that NAN converges to 0 as n approaches infinity. So how we should approach this? And in fact here, well, there are plenty of solutions to give to this problem, but I would like to show you one which will require a little bit the Cauchy interpretation of the convergence of series. So we will prove the following. So we show prove the following. We prove that I'm going to take the subsequence of odd terms and the subsequence of even terms, right, of NAN, and I'm going to show that both of these will converge to 0, and then this will imply that NAN will converge to 0, right? So we'll prove that 2n times a sub 2n converges to 0 as n approaches infinity, and that 2n plus 1 times a sub 2n plus 1 will converge to 0 as n approaches infinity. And once we do this, it will follow that NAN will converge to 0. And I'll leave this to you as an exercise to figure it out. Why is this true? But anyway, it's pretty trivial to prove. All right, let's prove the first one. Okay, let me let's look at the first part. Let's show these, that 2n a sub 2n will converge to 0. And here where the fact that is decreasing will come into play. This will be essential here. And we'll prove this. Okay, let's look at these terms. So I have, so we look at these terms, 2n times a sub 2n. So we have that 2n, a sub 2n. In fact, let me write them here. 2n, a sub 2n. This is greater or equal than 0, whatever. So I'm trying to bound this from above by something that will converge to 0. And this will be less or equal. I know that the sequence is decreasing, right? And I'll have n terms of these. So let's keep the 2 out. So this would be, okay, a sub 2n. Let me write it like this, a sub 2n plus a sub 2n. So I have here n terms. And since the sequence is decreasing, this will be less or equal than 2 a1 plus a2 plus, or maybe I should do it like this. Look. So maybe I should write here a sub n plus 1 plus a sub n plus 2 plus a sub 2n. So this is to the sum from k equals n plus 1 to 2n of ak. Let's write it in this way. All right, great. But what did we say about the convergence of series? We said that we're only going to take into account the first n terms, right? The partial sum. So a1 all the way up to an, and we're going to take into account this sum, right? For n large enough. So what is coming next by the Cauchy criterion, it doesn't really matter. Remember the Cauchy criterion, a series is convergent if and only if for all n, there exists an n epsilon such that n for all n greater or equal than n epsilon, and for all p, we have that x plus the absolute value of x plus x sub n plus 1 plus x n plus 2 all the way to x plus x sub n plus p is less than epsilon. So those terms all starting from n plus 1 all the way do not matter. So this is what happens here. So this guy, as n approaches infinity, will converge to 0, right? And this will converge to 0 as well. So by the squeeze lemma, this will converge to 0, right? So by the squeeze lemma, um, 2n, a sub 2n will converge to 0 as n approaches infinity. And we're done, right? Very nice trick, right? All right, so we're done with the first one. That's good. Let's see the second one. The second one will follow immediately from the first one, and let me show you why. Or you can mimic the same procedure, but I don't want to do that again. For the second part, we have that 2n plus 1 times a sub 2n plus 1. This will be 2n a sub 2n plus 1 plus a sub 2n plus 1. But now this guy here, it will be less or equal. Now we're going to use the fact that it's decreasing. This is 2n a sub 2n plus a sub 2n plus 1. And now guess what? This is greater than 0. Again, we use the squeeze lemma, so this will converge to 0. And these guys, you know that this guy will converge to 0. We know from previous. And also we know that this guy will converge to 0. So therefore, their sum will converge to 0. And again, by the squeeze lemma, this will converge to 0. So again, by the squeeze lemma, it follows that um, 2n plus 1, a sub 2n plus 1 will converge to 0 as n approaches infinity. And we're done. That's a very beautiful proof. Of course, there exists some other proofs. For example, there is one using the Cauchy condensation criteria. You can try that as well. There is another one using ratio test and so on. But anyway, I'll leave them to you to use to solve this particular problem. Now, I would like to move to some other problem. And so problem number 3. And this was a Putnam problem. In fact, let me mention this. So this was a Putnam A2 2011. All right. And the problem states the following. Let me see. So it says that let A1, A2, and so on, and B1, B2, and so on, be sequences of positive real numbers such that A1 equals B1 equals 1 and Bn equals B sub n minus 1 A sub n minus 2. That's funny. For n, 2, 3, and so on. Assume that all these bj's, let's say, are bounded. Okay. Prove that that this is sum, which is given by this series. So this series, so the sum of 1 over A1, A2, AN converges, and we should evaluate S. Okay, so this is the Putnam problem. So this is the statement. Yeah, that's correct. All right. Well, it kind of rings a bell to us. Maybe, I don't know. It kind of looks like telescoping sum to me, right? You see, I have that product 1 over A1, A2, AN, and I have this funny recursion which involves these two sequences, right? We look at this guy here. Look at this one guy here. And what I'm asked to do is to evaluate that in terms of the product A1, A2, AN. So maybe we should, the only option we have here, maybe we can express in some way, maybe this guy here, in terms of the recursion here. So let's see, let's think of it. Let's see. So so let's rewrite this sequence Bn, right? Okay. So we can rewrite here this the AN in terms of Bn. So we have that that AN is nothing else than just Bn plus 2 over Bn minus 1, right? For all n greater or equal than 2, right? So we have this. So maybe we can now write this. So this implies that, so this gives us, and now let's write that guy, 1 over the product, 1 over A1, A2, AN is nothing else. And now let's just use this sequence. Okay, let's write it. So it's 1, so A1 will be, so sorry, n equals 2. Okay, so we'll have 1 over B2 plus 2 over B1. So it will be B1 over B2 plus 2 times B2 over B3 plus 2, sorry, times, and we keep going. The last one is Bn minus 1 over Bn plus 2. All right, so we have this, right? I just used the relation above. And this guy here, if we look closely, this will give us, so, and now we can group them, you see? So I can write this in the following way. So let me write it like this. So B2 over B2 plus 2 times, And now I'm going to write this B3 over B3 plus 2. So I'm just going to group them like this. And I'm going all the way to Bn minus 1 over Bn minus 1 plus 2. Okay. And now let's see, what else do I have? B1 is 1. Okay. Okay, that's great. So I got to get rid of it. So this will be B sub n plus 2, right? Bn plus 2. Okay, that's beautiful. So we have that. Oh, well, if you look at this guy here, you can just observe that this is a telescoping sum, because you can say that this is 1/2, and I would like you to pay attention here because it's a crucial moment in the economy of the problem. So this would be B2 over B2 plus 2 times all the way to Bn minus 1 over Bn minus 1 plus 2, and now minus B2 over B2 plus 2 times all the way to Bn over Bn plus 2. You see? Because I have this term here, that was the crucial observation, that this term actually will give me, well, of course, you have 1/2, so that things will be clear. This is exactly the term that will give me that these are telescoping. All right, that's beautiful. But this point is quite clear, you see. So now let's define, let me just clear up the notation a bit. So let's denote by, let's say, xn to be this product all the way to n, right? So b 1/2 times b2 over b2 plus 2 times bn over bn plus 2, right? So I have this product, and we have that. So let's see, what do we have? So I know that this is, so we have that 1 over the product, so a1, a2, an. 1 over this guy will be nothing else than xn minus 1 minus xn for n greater or equal than 3. So we have this equality here. Well, this is beautiful because you see, and because I will write this, well, I have to compute the series of this, so this will imply that. So what should I say? Okay, let me write it in this way: 1 over a1, a2, a3 plus 1 over a1, a2, a3, a4 plus so on, plus 1 over a1, a2, an, right? This guy will be nothing else, if you look, and x2 minus x3 plus x3 minus x4, right? If we use the relation, this one above here, plus the last one will be xn minus 1 minus xn. And these two are telescoping, so this guy will go with this guy will go with this guy, this will be, and the only thing that will remain here will be this last one and the first one. So this would be nothing else. Okay, let me write it with red, x2 minus xn, right? And this guy, if we go back to our sequence, remember that xn is this product here, right? It's 1/2 times that product. So this would be nothing else. So x2 will be 1/2 b2 over b2 plus 2, all right, minus xn. Minus xn, which is that. So this is, we can write b2 in terms of b1, right? Because we know the recursion. So this would be, let's look at the recursion. So b1 is 1, a1 is 1. Okay, so it will be 2. So it will be 1/2 times 1 minus 2 over b2 plus 2, right, minus xn. And this would be nothing else than just 1/2 minus 1 over b2 plus 2 minus xn, right? So we have this. And now, of course, this part with 1/2 minus and that part with 1 over b2 plus 2 will be finite. So let's write it. So we have that, let's write it in this way. Let me write it. How should I write it? Okay, I'm going to write it with the XSM, right? So this guy will be the sum from n equals 1 to m of 1 over a1, a2, an. So let me consider the partial sum of this. And this would be, if we write it, it's 1, because it's 1 over a1, which is 1, plus 1 over a2, plus, and now starting from the third one, it is 1 over a1, a2, but a1, since it's 1, you have only 1 over a2 plus, and now look here, I'm going to be very careful. I'm going to write it in this way. Let me write it in this way. So I'll have here 1 over a1, a2, a3, plus all the way to a1, a2, an. Okay, so I have this here. Okay. Let's see. And this would give us, so this is, so this is 1 plus 1 over 1 plus 1 over a2. And okay, and now we're going to use the telescoping thing. So that would be plus 1/2 minus 1 over a2, right? Minus xn. And this would be nothing else if we add up everything. We know that this is, so it will be, okay, these two guys will just go away. So it will be 3/2 minus xn. And now we need to take care of this guy xn. Let's see what happens to this sequence. It's very important to see. So maybe let's go back. Who is this xn? Was this guy here. Keep that in mind. This was our guy xn. So maybe we could do something. Well, it kind of rings a bell to me, to what we should do. Maybe we should bound it. We suspect that this xn will converge to 0. So we show that. So I'm curious about this guy. Now we show that xn converges to 0. All right, but there is one thing that we haven't used so far, and let's go back to the problem. You see, in the statement of the problem, we have the following. We have that these two guys here, these guys, bj's, are bounded. So we would like to use this. We haven't used it. We haven't used the fact that this is bounded. So let's use it. So let's see. So we know that Bn, all these terms of the sequence Bn, so is are positive, but also less or equal than m for some positive m, positive real m. All right, and now let's look at the product. So now we have that xn, right? Which is the product of, okay, let me write it again. Right, there's this product here. This will be, since I know that so I know that Bn is less or equal than m. So this would be, let's look carefully here. Then what? Then so I can bound this by, so Bn, oh, okay, that's, so, okay, so it will be m to the power k minus 1, let's say. So I have here yeah, m to the power m n minus 1, right? And these guys here will be m over m plus 2 to the power n minus 1, right? Or if you want, we can write this as m over m plus 2 to the power n minus 1. But this guy here is between 0 and 1, so this will converge to 0 as n approaches infinity. And again, this will converge to 0 as well when n approaches infinity. And by the squeeze theorem, guess what happens? Again, this will hold true. So this will approach to 0 when n approaches infinity. So again, by the squeeze theorem, it follows that xn converges to 0 as n approaches infinity. And we're done. And now clearly, so if we look, so Sm, so as m approaches infinity, it follows that the sum of the series, that S is 3/2, and we're done. That's it, right? The sum of the series is 3/2. So that was a problem. It was a bit tricky, I would say, for an A2. That was back into, let me see, when was it? In 20, this was in 2011. Yeah, the Putnam that year wasn't the easiest one from what I've seen. So you could have gotten, got a in top 10% with only one problem from what I remember, with 11 points actually, or 12 points, something like this. Anyway, okay, so this was the problem, and I have another problem here on my list. This is a tricky one too. I would say, if you know the trick, I think it's easier than this problem, but anyway, you'll decide for yourself which one is easier. So let's see, this was problem number 3, now problem number 4. Problem number 4, which says the following. So this was a Putnam A3 into 2014. The problem says the following. So let A0, in fact, it's a pretty standard problem, if you ask me, and AK, because the recursion rings a bell already, AK is A sub k minus 1 squared minus 2 for k greater or equal than 1. And now, again, we would like to compute the sum of the series. So compute this guy here. So this product, this infinite product, in closed form. All right. You see, This is pretty standard because usually when you have a recursion like this, so you can already find the sequence. And okay, I will leave it to you. So by induction, by an easy induction, I would say, one can show that that A sub k is nothing else than just 2 to the 2k plus 1 over 2 to the 2 to the k, or all k greater or equal than 1. Well, you can prove it by induction. I'll leave it to you. So this would be an exercise for you. And now once I know this, I already know what to do. So now you'll see I only need this and another thing, and that's pretty much it. That's the problem. You'll see that I will discuss about an infinite product here. So let's see. So we have now this guy 1 minus 1 over ak. So this guy, right? So this would be, if we do the algebra, it's 1 minus 1 over that thing. So this would be what? 4 to the k plus 1. So it will be 2 to the 2 to the k over 4 to the 2 to the k plus 1. All right, so we have this. And now if we want to do a little bit more of algebra, and why not? This will be 4 to the 2 to the k minus 2 to the 2 to the k plus 1. Everything over 4 to the 2 to the k plus 1. Oh, great. All right. And now we would like to see something here, because I think we can rewrite this a bit. We can if we multiply by 2 to the 2 to the k, so we have the cube formula. So we multiply by 2 to the 2 to the k plus 1. So this would be, okay, let's write it. So this would be 2 to the 2 to the k plus 1 times 4 to the 2 to the k minus 2 to the 2 to the k plus 1, right? Everything over 4 to the 2 to the k plus 1 times 2 to the 2 to the k plus 1. Which will give us here, so this would be, since I have the cube formula, this will be a to the 2 to the k plus 1, everything over this guy, 4 to the 2 to the k plus 1 times 2 to the 2 to the k plus 1. All right, finally, so we can write it in this form. And I think we can get going from here. And now we have one more ingredient that I would like to use here. And we will use the following formula. Well-known product formula. Okay, and the formula is the following. So the product over all k from 0 to infinity. Well, actually, no, I don't want to use it like a series to, let's say, m, right, of x to the 2 to the k plus 1. So this guy here, if you multiply all these terms, it will give us x to the 2 to the m minus 1 over x minus 1. Well, it's pretty easy to see. We have this formula, right? And now, Let's see. So we would like to use this. And we're going to do the following. Well, the proof of this formula is pretty easy. You just multiply x minus 1 to this, and then everything will just, when you foil everything, they will just they'll be telescoping sums, and everything will just go away except the first one and the last one and the first one, which will be x to the 2m and x to the and 1, because the last one will be 1. Anyway, it's pretty easy to see. But that's a good identity to know. And as you can see, it will be very useful here. So let's figure it out. How are we going to apply it in this situation? So let's see. So I know this guy here. So this guy is this guy. All right. And now let's see. So we have that. Let's see, what do we have? We have the product. So let me write a product. So that the product from k equals 0 to m of 1 minus 1 over ak. This guy is you see, now I'm gonna perfect. So now we apply this identity, because all these terms, if you look here, they're in terms of yeah. So I have the products of let me see. So I have let's write it. So this is the product from k equals 0 to m of 1 minus 4 to the 2 to the k, plus 1 times 2 to the 2 to the k plus 1, everything over a to the 2 to the k plus 1, right? Okay. And now if I do all this, this would be nothing else. And by applying this identity here, this will give us exactly. So this would give us what? It will give us, by applying the identity, this will give us what? 8 to the 2 to the m plus 1, sorry. Right? And here I think I made a mistake. This identity is not like that. I think it's m plus 1 here. Yeah, that's more correct, yes. Because when you multiply the first one, when you have x minus 1 and you multiply, you see the first term, the product there, you'll have the term x to the 2 to the m, and then you're going to multiply by x, so you'll have x to the 2 to the m plus 1. Yeah. Okay, so this will be a to the 2 to the m plus 1 minus 1 over 8 minus 1. Sorry, minus 1 here. Over 8 minus 1 times, let's see what else do we have. So we have, okay, yeah, this will be turned upside down, so it will be 4 minus 1, again, the same product, over 4 to the 2 to the m plus 1 minus 1. And now also we have this for 2, so but it will be on the bottom, so it will be turned upside down as well. So it will be 2 minus 1 over 2 to the 2 to the m plus 1 minus 1. Oh my goodness. And let's see what this gives us. So we'll have 3. This will be 7. Okay, that's good. 3/7 times this guy times, let's write this, a to the 2 to the m plus 1 minus 1 over 4 to the 2 to the m plus, let's be careful here, to the m plus 1 minus 1 times 2 to the 2 to the m plus 1 minus 1. Okay, so we have this. And now we know that, but, okay, I think it's clear. Anyway, we can just neglect that. We can take, but as n approaches infinity, let me write it in this way, h to the, okay, a to the power n over 4 to the n minus 1 times 2 to the n minus 1, right? Which will be nothing else than just 8 to the power n over 8 to the power n minus 4 to the n minus 2 to the n plus 1. So as n approaches infinity, this guy will approach what? Well, it's quite clear when you factor 8 to the power n on the bottom, you will have 1. So this would be 1. So finally, this gives us that the sum from k equals 0 to infinity, let's write it in this way. So the sum of the series is nothing else than just 3/7. And that's it. We're done. So that's the problem. You see, basically the problem had only 2 ingredients. To know that by an easy induction you can prove this, you can guess the recursion, which in fact it's important, and the fact this identity. Once you know these 2 facts, the problem becomes just a computational problem. So, and this was a Putnam A3 into 2014. 2014 was also a difficult exam, I would say. So these are the two things. Anyway, we'll compute the sum of other series when we will talk about when we have more material covered in analysis, such as the differentiability. When we deal with some integrals, you will see that there are plenty of other ways of computing the sum of series. Well, in these 2 examples that I did, we had kind of, in the first problem, it was a telescoping sum, and then in the second one, I could guess the recursion, and that's it. All right, guys, I think we can wrap up for today's recitation. I'll see you next week. Bye-bye.